Ay, ya está grabando.
Sí, ya está
Así es.
grabando. Ujú.
Ok, perfecto. Muy bien. La Universidad Autónoma de Chihuahua, a través de la Secretaría de Investigación y Posgrado de la Facultad de Ingeniería, tienen el honor de abrir el espacio de nueva cuenta del ciclo de Seminarios de Investigación 2021-B. Este día nos complace recibir a nuestro invitado de lujo, el doctor David Jáuregui, quien es ingeniero civil por la Universidad de Nuevo México y de igual forma tiene una maestría en estructuras por la misma universidad. Realizó su doctorado en estructuras en la Universidad de Texas en Austin. Cuenta con una gran experiencia profesional como investigador y profesor del Departamento de Ingeniería en NMSU. Actualmente es el jefe de dicho departamento y ha sido profesor en más de 20 materias diferentes del área de estructuras, tanto en licenciatura como posgrado. Tiene más de 50 publicaciones de tesis, artículos y ponencias en diferentes congresos, así como capítulos de libro y publicaciones de alto impacto. Es miembro de distintas asociaciones de interés de la ingeniería y su actividad con el programa de ingeniería en la universidad ha sido constante desde el año 2000 a la fecha. Cuenta con más de 25 direcciones de tesis y ha obtenido reconocimientos por su excelente desempeño. Gracias al convenio que existe entre nuestra universidad y NMSU, nos sentimos muy honrados de que el contacto sea el doctor David Jáuregui y que hoy esté presente en nuestro seminario de investigación. Le damos la bienvenida a su conferencia titulada Bridge Engineering at NMSU. Antes de continuar con la conferencia, por favor recuerden los alumnos que están interesados en que el evento sea tomado en cuenta para su carnet, tomar la evidencia de que estuvieron presentes y hacer un breve resumen de la conferencia impartida y enviarla al encargado del carnet. Por favor, no olviden apagar sus micrófonos para no interrumpir la plática y favor de esperar la sesión de preguntas y respuestas para poder participar al final. Le damos la bienvenida. Welcome, Dr. Jáuregui. Now is your turn and all yours.
Okay. Well, thank you very much. I really appreciate, and as I had mentioned to you, I will be presenting in English. I hope that's okay. I do speak a little Spanish. Le quería dar las gracias por la invitación. Estoy muy honrado para poder compartir el trabajo que ha hecho y gracias. So what I'd like to do first, let me go ahead and share my screen so I can get things going here. Let's see. I'm just gonna make sure that you could see my presentation and also hear it.
Okay, we can see it. Yes.
Okay, you can see it?
But can you in full screen, please? Oh, yeah. Right.
How's that?
Yeah, great.
You can see it okay?
Definitely, yes.
Okay.
Yes, we can.
Okay, well, before I get going, I'd first like to thank Dr. Espejel Garcia and also Dr. Villalobos Aragon for this invitation. Just to give you a little bit of background, we've had a collaboration with University of Chihuahua for many years now. We've had a joint PhD program. And I'm honored to see that Dr. Jorge Marquez is in the audience. I worked with Jorge and I'm very honored to see that he's here. We also have a joint Bachelor of Science and Master of Science degree, where we have students that transfer from University of Chihuahua to NMSU, and that program is growing every day now. So we're very, very proud of that. And so I'm going to give my presentation. If you could, towards the end, if you would please note your questions and then ask me at the end, I think that would be the most appropriate. And so once again, thank you for the invitation. And as you see here, I'm going to be talking about bridge engineering at New Mexico State University. And the first thing I'd like to do is I want to talk about the past research that has been done at NMSU, present research, and also the future. And then I'm going to discuss a project that was recently completed here at New Mexico State University on the topic of bridges without plans. And so what basically this means is that bridges without information. And I'll give a little bit more detail on that as we progress. So to get things going, I want to first tell you, New Mexico State University has been involved with bridge engineering for many years. It actually started in the late 1960s and the early 1970s. And my mentor was actually Dr. Kenneth White. And Kenneth White, he came to New Mexico State University at about the same time that there was a significant bridge failure. And this was in West Virginia. And this was the Silver Bridge over the Ohio River. And to let you see about what happened during this particular failure, I'm going to show a short video. So let me go ahead and show that. Oops. So here goes the video. It will soon start playing.
The road hung from a simple, elegant chain design made possible by a new type of high-carbon, high-strength steel. It made quite an impression and was known as the Silver Bridge. If the weight of traffic had been the culprit, the long, thin shank would have broken, not the circle of the eye-bar where the steel was at its thickest.
So if the eye-bar was broken just from excessive
the bridge was falling toward me like dominoes. And by the time my car did stop, my wheels was just right on the...
37 cars and trucks fell into the river. Charlene's car hung precariously on what remained of the bridge. It was the worst road bridge disaster in U.S. history.
Expand the Ohio, near the town of Point Pleasant, they say, with a heavy load of traffic, began to swing and sway.
had been photographed as they took it out.
This is the broken eye-bar. Each eye-bar was a link in a kind of giant bicycle chain. The massive linking circles were at either end of 50-foot-long shanks that held up the bridge, but the tiny, undetected crack caused a single link to fail. When the chain on one side of the bridge snapped, the other chain could not take the weight of the bridge, and down it went.
So, can you hear me still? Can you still hear me?
Yes, we can hear you.
Okay. Okay. So that was a video of the Silver Bridge over the Ohio River, and you could see that it resulted in 46 people losing their lives. And because of this failure, in the U.S., they started the National Bridge Inspection Standards, which are related to safety and maintenance of bridges. And so once this started, New Mexico State University starting working with the New Mexico Department of Transportation, and now we are a university that actually conducts bridge inspections for the state of New Mexico, which is a very unique program because we hire undergraduate students, 4 undergraduate students every 6 months and they're the ones that actually help with the inspections. So it's only one of its kind in the US. And so something that we provide experiential learning co-op experiences for our students. A couple of other failures I wanted to talk about. There was the Sunshine Skyway Bridge in Florida in 1980. That bridge failed due to pier protection. The bridge was hit by a barge. Then we had the Myanes River Bridge in 1983. This was in Connecticut. And this was a fracture critical bridge in which, much like the Silver Bridge, if one of the components happens to fail, the whole bridge will collapse. We also had the Schoharie Creek Bridge in 1987 in New York. This bridge failed due to scour and undermining. This is where water gets under the structure and starts to basically remove the soil from underneath the piers and the abutments. This is a very common problem in areas where there's a lot of rainfall and flooding. And then most recently, we had the I-35W interstate failure. This was in Minnesota in 2007. And this particular bridge failed because of the condition of the gusset plates. And so, all the different provisions from the US have changed because of these failures. And this kind of gives you a progression of all these bridge failures, starting off on the Silver Bridge, moving on to the Myanes River, I-35W. And then in 2013, there was a bridge that failed in Washington over the Skagit River. And that was because a vehicle hit the bridge. It hit a truss bridge and the bridge collapsed. So anyways, that's I like to give that introduction because our work at New Mexico State University focuses on inspection, evaluation of infrastructure. We do a little bit of design and new construction, but a lot of our research has to do with evaluation. And so what I just talked about here is the inspection and rating of highway bridges. Like I said, we've been doing this since 1967. We also move into the area of higher level evaluation of reinforced concrete slab, steel girder, and pre-stressed concrete girder bridges. What I mean by higher level evaluation is we're looking at three-dimensional modeling and also load testing of bridges, which I will talk about in more detail here in a few minutes. We also have projects related to the retrofit of bridges using carbon fiber reinforced polymer materials, load rating and fatigue evaluation of railroad bridges, riveted connections of steel arches. This is a project that we did for the Los Alamos National Laboratory, which is located in Los Alamos, which connects the city of Los Alamos to the lab. And then another area, which is ultra high performance concrete for pre-stressed concrete bridge applications. We've been using this for looking at concrete strengths ranging, a typical concrete strength is about 10,000 pounds per square inch. And the concrete that we're producing at New Mexico State is double that. We're looking at 20,000 pounds per square inch. And that's the material we're using for bridge beams. And we're also using that material for overlays of bridge decks. And then the last three that we have going on is we had a masonry arch bridge evaluation using photogrammetry. This was a project where I collaborated with the University of Vigo in Spain. And they were using photogrammetry and LiDAR to basically come up with a geometry of these old masonry arches. And we look at establishing the capacity of those bridges based on the modeling that was done by photogrammetry. Bridge stability during demolition, there was a project that I was involved with where they were removing the bridge. They were taking the deck off the structure and the girders collapsed during that demolition process. And as a result, they had me investigate that to make sure that things were done properly in the future. And then the last project that we're working on right now is on the permitting of oversized and overweight vehicles. our limit of bridges legal loads is 80,000 pounds. But due to the work that's being done in New Mexico related to the oil and gas industry, the fracking, they need very large vehicles to transport the equipment. And we're getting loads in the millions of pounds. And what's happening is this is creating damage to the infrastructure, in particular bridges and pavements. And we're coming up with a fee structure. We will need to charge these vehicles so that way we could basically retrofit, rehab, or replace bridges in the New Mexico area. Okay, so let me just briefly talk to you about the bridge inspection program. So I'm the PI for this project, as I mentioned to you. We have a program coordinator, we have 2 team leaders, we have 4 co-op students that participate in this project every 6 months. So over a given year, we have 8 students that participate. And I like to mention this program because if you're a student from the University of Chihuahua and you happen to come to NMSU, you can participate. In fact, I have a couple of people that are interested right now, and you would be hired for 6 months and you'd be able to get some experience, which would be very useful for future employment. We inspect about 400 bridges every year, including fracture critical bridges, such as the one that you saw in terms of the collapse. Right here, you could see the Taos Gorge Bridge. That bridge we inspect every 2 years, and we just finished inspecting that. That is 600 feet above the ground level, which is very high, and it's requires that we actually use climbers on that. And we have an underbridge access unit. You can see people here inspecting the structure and getting ready to go down underneath the structure. The other thing that I wanted to mention to you, and particularly those that are interested in bridge inspection, we also offer training that's offered in January and May. This is for 2 weeks. And once you complete this course, you are now certified to be a bridge inspector in the US. We also offer a 3-day refresher course every 3 years, and the next one will be offered next year in 2022 in December. So these are some of the activities that we are involved with in terms of the bridge inspection side. And so just to kind of give you an idea on the bridge inspection side, the things that we do is we have to basically look at the bridge component here, and then we have to assign a condition state. Condition state 1 is good, condition state 2 is fair, condition state 3 is poor, and then condition state 4 is severe. And so our students and the engineers have to go to all bridges and essentially collect this type of information. The New Mexico DOT will then get this information and they'll use it to plan the use of their funding. So for example, if you have a bridge component that has a lot of the area in condition state 4, then what they would do is they would say, we need to replace the bridge deck. Okay, and so we have to inspect bridges every 2 years. So each one of our bridges are inspected every 2 years. And so this area of work is a very much related to forensic engineering, where you're evaluating infrastructure and making sure that it's safe for the public. All right, so the next area I'm going to talk about is our bridge evaluation program. And on our bridge evaluation program, it essentially involves coming up with a capacity of infrastructure, so that way we could set limits in terms of how large the loads that can go over our bridges. And so the one that I want to talk about today is called the load rating of pre-stressed concrete bridges without plans. And you'll see that it involved load testing and also some non-destructive material evaluation. I'm going to focus on pre-stressed concrete bridges, but we also did reinforced concrete, steel, and timber bridges. And that included field visits and as-built plan development. Okay, So I'm just going to say this real quick, just in Spanish, so that you understand what the topic is. It's really the evaluación de puentes sin planos de diseño. So no hay información en estos puentes y por eso hay muchos problemas con la evaluación. Okay, so just so that you kind of see what the topic is. All right, so the bridge testing equipment that we use, you can see these are sensors that we attach onto the girders. This is a product that we've been using for many years. It's a structural testing system that is provided by a company called Bridge Diagnostics Incorporated. And we work very closely with them. And one of the recent articles that have come out has been related to this particular project. So let's go ahead and get into that particular project. And so as you see here, this is going to be the evaluation of pre-stressed concrete bridges without plans. And once again, evaluación de puentes preforzado sin planos. Okay, let me just talk about the introduction. Okay, so right now in New Mexico, there's bridges without design plans are a major issue. Approximately 10% of bridges do not have design plans. So in the US, there's over 600,000 bridges throughout the whole country. So of those 600,000, 60,000 do not have plans. So it's very difficult to determine the capacity. Okay, and so on many of these bridges, they're older, what are called off system. They're not on the interstate. Okay, they're owned by a city, they're owned by a county. And so the bridge plans have just disappeared. And so this is a challenge, right? How do we determine the capacity? We can't do an analysis because we don't know the concrete strength. We don't know the rebar. There's a lot of things that we don't know. So we did this project for the New Mexico DOT to come up with a plan so that they can evaluate these types of bridges. All right, so just to give you an idea on the literature review, so prior to 2000, the year 2000, there's been a lot of proof testing. And this is in Alabama, Florida, Michigan, and New York. And what a proof test is, you have to continue to load the bridge as much as you can until it becomes nonlinear. So if you look at the elastic response, at some point it's going to go nonlinear, and that occurs usually when the concrete cracks or you have some type of yielding. However, most of those proof tests were done on reinforced concrete and on steel bridges. Very few are done on pre-stressed concrete. And the reason they're not done on pre-stressed concrete is because you don't want to crack the beams. So we figured we need to find a way to apply load and also make sure that the beams don't crack, okay? Other states such as Iowa, Delaware, and Vermont have also sponsored bridge testing research in addition to those 4 states that I just talked about. Georgia also recently did a project, but most of the testing that they found was diagnostic testing. And what diagnostic testing is you use a very small load to determine what the behavior of the bridge is. You then calibrate a finite element model, and then you use the model to determine what the capacity of the structures is. We also had a European project. We found that where they did a study on diagnostic and proof load testing. But once again, it was mainly reinforced concrete and diagnostic testing that was used. We're looking at pre-stressed concrete and proof testing. I'm going to take a quick drink here. What's the research need and the approach? We're going to be using the AASHTO Bridge Evaluation Manual. For those of you who have taken bridge engineering classes, you're familiar with AASHTO. That's the American Association of State Highway and Transportation Officials. And we're going to be looking at Service 3 limit state. Okay, and this relates to concrete cracking. And it's going to be aside from using the Strength 1 limit state. Okay, so we're going to be looking at Service 3. All right, so let me show you the first bridge we looked at. This is a very short bridge. Excuse me. Very short bridge, and you could see that the top surface of the beams, these are pre-stressed concrete, and you could see the top condition. So you could see all these individual beams next to each other, and the connections are damaged. You could see all these damaged connections. So once again, we don't know what the strength is of the concrete. We don't know if there's rebar. We don't know if there's pre-stressing strand. All of that is unknown information. And these bridges are very common in Las Cruces because there's a lot of agriculture. And so in order to get over like some of the channels, what they'll do is they'll go find some old beams and they'll just span it over the channel, and they won't even really design the bridge. It's just like old beams, and they're just trying to salvage those and use it as a bridge. Okay, so once again, you can see now what the challenge is. What's the capacity of these bridges? So to kind of give you a summary of what the bridge looks like, it's single span, pre-stressed concrete, 31-foot spans. The shear keys that are located on the top of the beams, they're damaged, as I had mentioned to you before. The good thing is that there's no flexural cracking on this beam. And so now we can proceed to evaluate the capacity. So the basic procedure that we followed is we're going to be using what are called Magnel diagrams. This is to determine basically the relationship between pre-stressing force and eccentricity of the pre-stress force and pre-stress force itself. We also use a rebar scanner to detect the steel so that we could actually get an idea of what type of reinforcement is in the beam. We then did a diagnostic load test, and then we used that diagnostic load test to plan a proof test. And on the proof test, we're going to put many trucks, up to 4, to basically show that the bridge can carry a prescribed amount of loading. So on the estimate of the pre-stressing strand, these are the equations that we used. So if you look at P1, okay, P1 and P2 have to do with the requirement for pre-stressing stress at release. So this is the amount of pre-stress we need and the limit state associated with transfer of the pre-stressing strands. This is when the strands are cut in the yard, in the precasting yard, and we want to make sure that it does not exceed the allowable stress. So if you could see here, the only thing we have is what is called the pre-stressing effect here, and then we have dead load. Okay, so the dead load moment is the only thing we're looking at in this particular equations, these first 2 equations. And this one is related to the bottom flange stress, and this is the top of the flange stress. P3 and P4, those are related to service loads. So now you have moment total, which includes dead load plus live load, and then you have a K factor, which is going to be related to pre-stress losses. Okay, so we now have to calculate what the pre-stress losses in the service condition. So those are the general equations that we used. All right, so you could see the different lines here. You have the force in the pre-stressing, and you have the eccentricity, and those are the 4 lines. So you can see the green line here represents, or actually the blue line here represents at release, the red line, and then the green and the blue are at service. Okay, so this area that you see is the area where you have satisfactory design. Okay, so if you look at the top point, that represents a low pre-stressing effect, high eccentricity, and then the bottom point represents the high pre-stress and the low eccentricity. All right, so most bridges are designed for the low pre-stress and high eccentricity, and really what you're doing is you're putting the strands as far as possible from the center of gravity, so that way you have a larger lever arm and then you lower the amount of pre-stress that you need, okay? And you see here that this was developed for the H20 design truck. All right, so these are the results. So what you see here in the yellow, okay, this is the yellow area. The low pre-stressing effect showed that I needed to develop, you need to develop about 116 kips of force, okay? And the eccentricity of that, or the number of strands, is gonna be about four strands, and the eccentricity is about 10 inches, okay? So this is just an estimate. What we're showing here is that we need 4 strands, okay? We need 4 strands for the H20 load, and then for the HS20 and the H15, you needed 5 strands and down to 2. So what we're thinking is we need between 4 and 6 strands, okay? So that's the amount we're expecting to show. And what we were able to do is estimate how many strands you need. So you need 6 strands, okay? You have 3 over here, that's at midspan, so it's gonna be located towards the bottom, and then 3 at the end, and they're harped, okay? And that's to control the end stresses. So in order to verify this, we used a Hilti PS250 ferroscan. And what this is able to do is it's able to scan for rebar, okay? And it's also, we're also looking to see if we can use it for pre-stressing strands. One of the limitations is that the reinforcement must be between 0.4 and 2.4 inches from the concrete surface. And it's mainly for mild steel reinforcing bars, okay? Not necessarily for pre-stressing, okay? So let me show you, this is, so here you could see this is the side view of the beam, okay? This is the side view of the beam. And this is the scanning of the side of the beam, okay? So you could see here, these are the stirrups, okay? The ones that you see here, you could see the stirrups. And then this is right here is the pre-stressing. You could see that they're bundled together towards the middle of the beam. And then as you start getting towards the end of the beam, they start to deviate. So you could see the 3 strands. You have 1 strand here, 2 here, and then they, as they come over here, they come together in order to increase that eccentricity towards the middle. All right. So now that we know what the beam looks like, the next thing we did is we figured out what is the cracking moment. All right. So what we wanted to find out is how much moment and therefore how much load can we put on this beam before it cracks, okay? Because the beams are not cracked, and we don't want to crack them when we go and do our load test, okay? So we need to come up with an estimate of what that cracking moment is. All right, and here it is right here. This is the formula we use. We have the section modulus, effective pre-stress, the area of the cross section, eccentricity, and then the cracking stress, the modulus of rupture. Okay, I'll go ahead and skip this one. So this is the, what we have here is the estimate of the cracking moment. So here is the cracking moment, 148 kip feet. Our dead load moment, this is the weight of the beam itself. That's the moment caused by the dead load. We get about 36 kip feet. So that means we have about 113 kip feet before the bridge cracks, okay? And what we're anticipating is that the moment due to the truck is going to be causing about 42 to 93 kips, okay, so kip feet. So that means that we're not going to crack the beams. So we have to convert that now to the available strain, which is about 530 microstrain. And this is what we're expecting as far as the truck, okay? So let me show you next. So this is the cross section of the bridge, okay? And so you have 9 beams across the cross section, and all these places where you see the circle is a strain gauge. So we're monitoring the strain at those locations. And then on the side, you can see that you have a strain gauge on the bottom and also on the middle of the cross section, so we can figure out where the neutral axis is. So now we're looking at the cross section, and this is where the trucks are going to go. okay? We have 2 trucks that we're gonna put on the bridge, and we're gonna make sure that we check how much strain is being measured by the sensors, okay? But when we first did the test, this is the available strain, about 530. So that means that if we exceed 530, we're gonna crack the beam, all right? And so the largest one we got was so on one truck path, we got 200 microstrain, 150. With 2 trucks, we got 265, and then we got 312, okay? So that is below 532, and sure enough, we did not crack the bridge. So now we can move on to the proof test, where we're gonna put 4 trucks, okay? And so this is the proof load test, and we changed the instrumentation a little bit because right at this location, all the connections were damaged, okay? So we damaged all those connectors, or we did it, and it was already damaged, okay, just due to use of the bridge. But notice how we have a lot of sensors right in this region because we don't want to exceed the available strain there. Okay, so what you see here is just the bottom side of the bridge, and you can see the sensors. You have a sensor here, a sensor here, on the over the height of the cross section, and we're looking at strain all across the width of this bridge. And before we did that, another thing we had to do is we needed to make sure that the bridge would not crack due to shear forces. So under our truck, we were expecting a maximum shear of about 26 kips, and our shear capacity, according to this equation here, which is a web shear cracking force, we're looking at about 27 to 42 kips. So that means that it's not going to crack due to shear, okay? However, we might still crack under flexure, and that's what we're going to check. So these are the truck positions. And let me go ahead and just show you. These are, so we have the trucks. We're backing up the truck at this location. This was with 1 truck. This is with 2 trucks back to back. And see, you could see right here, you could see the crack, you know, there's a failed connection, okay? So basically you have like 2 halves of the bridge acting independent. They're not connected, okay? So we had to be very careful not to exceed that strain on the bottom. Here's 2 back to back now. So if you look before, these are side to side. Now we have it back to back. And now we have 4 trucks, okay, back to back on this span. So that's a lot of load. And this is the most load that this bridge has ever had. And so again, we wanted to make sure that it didn't that it didn't fail. All right, and these are kind of how we did it. So this was with 1 truck. This is with 2 trucks back to back in just 1 lane. And then over here we have 2 trucks, and then we have 4 trucks. Okay, so we tried a lot of different loading arrangements. And so this is the amount of strain we got. So you could see that our available strain was 530, and look at how close we got, 528. So that means if we don't stop the truck, it's going to crack. It's going to crack the bridge. And so we stopped it. And that's the reason, if you look back here, see on this first one, we took the truck all the way to 14 feet. Here we did only 10 feet. We could not take it all the way because we had 2 trucks on there, and we'd fail the bridge. All right, and so you could see different truck arrangements, and that's the reason we had to stop the truck from going any further. And that's the reason, if you look back here, that's the reason that we didn't move the trucks any further. Okay. All right, so now we've stopped the trucks. We know how much load was on the bridge. So now we can come up with a load rating, and we had to come up with a moment equation, which is the target load. And you have this adjusted target load factor. We have different types of legal loads some that are specific to New Mexico, and then also some that are specific to the Federal Highway Administration. So this equation predicts what is the level of load that we need to put on the bridge to prove that it could carry the legal load. Okay. And then we have some adjustment factors. We have to adjust the load. If we have one lane loaded, remember we showed 4 different load configurations. 2 were one lane loaded, 2 were multiple lane loaded. So for one lane loaded, we have to increase that target by 15%. If it's non-redundant, that's another 10%. And we said it was non-redundant because the bridge girders were not connected. So one beam could actually fail. We did an in-depth inspection so we can reduce the amount of load by 5%. And then the average daily truck traffic was less than 1,000, so we can reduce it another 10%. All right, so these are the adjustments that resulted right here. Okay, and then finally, the final rating is we had a rating factor for operating. This is the largest load you can put on the bridge. We have the actual test moment, which we applied by the trucks, and the target. So think of it like this: if you placed 50 kips and the target was 40, then you were able to show that it could carry 1.25 the amount of load for the legal load. Okay, and then we had a final adjustment that we need to make for the safe posting load, and that's how much we can actually put on the bridge. Okay, so let's look at the final results. All right, so these are the final results. You could see here that these are the rating factors. So these are all the legal loads we did. We did HS20, type 3. These 3 right here are federal legal loads. These are New Mexico legal loads. And so what that means is we now have to put a load posting sign on the bridge for these 3 loads and these 2 loads. Right here, which is the type 3.3 and the New Mexico 2, we did not need to have a load posting sign because the rating factor was greater than 1. Okay, so think of it like this: you're basically going to have to put a sign in front of the bridge saying that this is the load limit, and these are the load limits for these different trucks. It ranges from 16.9 tons all the way up to 30 tons. Okay, so that was the study. It looks like I'm getting ready to I'm running out of time here at 4:45. But we did another test. This was a bridge that we did, which was a box girder bridge, but it's very similar. And so I'm not going to go into the details on that. What I'm going to do is I'm going to go ahead and go to the conclusions. So that way we can go ahead and not end off the presentation. So let me go to that slide. Okay, so the conclusions from our study was that conducting the load test based on serviceability was used to ensure the bridge didn't crack. We used strain gauges to monitor to make sure that we weren't putting an overstress. Diagnostic load tests were very useful for coming up with the proof loads, and we were able to show experimentally that the bridge could carry these loads, which was the whole idea behind the project. All right, and so with that being said, I'm going to go ahead and stop right there and see if there's any questions. Thank you, Daphne. I think I'm done. Are you still? Can you still hear me?
El micrófono, Daphne.
Oh, sorry, I was speaking and nobody can hear me.
Oh, you must. Yeah. Okay, you might have been muted. Okay.
Yeah. Well,
okay.
Thank you, David. To be on time. So let's start with questions. ¿Alguien tiene alguna pregunta? Es tiempo de que levante su mano, por favor.
And they can ask in Spanish. I'll do my best to answer in Spanish if they would like to have questions in Spanish.
Así que aprovechen y pregunten.
Doctor Márquez quiere preguntar, yo creo.
Sí, vamos, doctor.
Tiene apagado el micrófono, doc.
Igual que yo.
Igual que usted.
I'm gonna
Dr.
stop.
Jáuregui, good afternoon.
Good afternoon, Jorge.
How are you? It's a pleasure to have you here and to hear you again in this very good presentation that you already had. The only question that I would like to ask you is to see in how many bridges do you have experienced this kind of test that you already made? What is the, I will say, like the scale of measure of the media or the average of the load rating that you have already made in these bridges? Are they in New Mexico or somewhere else, or where?
Okay, yeah, so that's a good question. So Jorge, so really what that is so when I told you 10% of the bridges, that's 10% of the bridges nationwide.
Mhm.
Okay, so we're looking across the whole country. There's about close to 80,000. So I'd say about 80,000 bridges that don't have plans. So it's a big problem. There's a lot of bridges that exist in the US that don't have plans.
Okay, so are you going to continue with these plans? I mean, with these procedures to finish testing all of those bridges?
Well, no. See, you got to. The one thing I do want to mention is that those 80,000, some of them are pre-stressed concrete, some are reinforced concrete, some are steel, and some are timber. Okay, so for example, if you're looking at steel, steel, you don't have to do a load test because you can go out to the bridge and you can measure the dimensions of the steel because it's exposed, right?
Mhm.
So the steel, you can go take measurements. You can measure the flange width, the thickness of the flange, how deep it is. And so you could take those measurements, and you can also take out a coupon of steel. So you can go take out a coupon, take it to the testing lab, and then come up with a strength, right? The yield strength and the ultimate strength. On the deck, you can actually use non-destructive tests like what is it? A Schmidt hammer, Proctor test that you can come up with some estimate of what the strength is of the concrete. So with the strength of the steel, the dimensions, the strength of the concrete, the thickness, which you can measure, you can actually come up with a load rating just based off of analytical. You don't have to do a load test. Okay. The same thing could be done for reinforced concrete slabs. So reinforced concrete slabs, for example, you can use the rebar scanner to figure out what your rebar is, because it's very good for that type of evaluation. And then you can also come up with a strength. So the only ones that it's really used for are ones where you cannot measure the amount of rebar using a rebar scanner. Okay, because these tests are very expensive.
Okay.
Yeah, they can get very expensive. And then the timber bridges, the timber, you can go measure the dimensions and come up with a strength. So the only ones that it's really used for is pre-stressed concrete and maybe some older steel bridges.
Mhm. So in these cases, the limit state 3 is the only one that you, well, I think it is the one that you need to analyze the limit state number 3. You don't have to use the ultimum load, right?
No, actually, that's a good question. Let me tell you something. Let me show you something here. If you look down on number 4, I put here that so now that we have an estimate of how many strands, the strength, we can then go do a strength limit state. So we have to still do that, but that you can just do that analytically. Okay, yeah, because in order to figure out how much the bridge can carry experimentally at the strength limit state, I'd have to load it and I'd have to crack the beams.
Yeah.
But what you can do now is, now that you have an idea of what because if you think about it, when we go and do the load test and we're able to prove that the bridge didn't crack, you basically verified how much steel's in the concrete, what's the strength of the concrete, and now you can just do a typical load rating analysis to figure out what the load rating is at the strength limit state and make sure that doesn't control.
Okay. Thank you very much.
You're welcome. Thank you for coming, and thank you for your questions.
¿Alguien más que quiera preguntar? Si les da pena a los muchachos, lo pueden hacer a través del chat con toda confianza.
So as you asked there, Daphne, who's the, can you give me an idea of who's attending? Like, are these master students, undergraduate students, PhD students? What is the makeup of the audience?
Okay, I think we have undergraduate students from, I don't know, 8th semester or something.
Okay.
And from graduate from, yeah, I don't know, somebody from graduate programs.
Okay.
Here? Yeah.
Yes.
I think.
So okay, very good. So we have undergraduates and graduates.
Yes.
Very good. So like I said, there's room for you here at New Mexico State University, and that because we like to work with the University of Chihuahua quite a bit. So hopefully I get to see some of you.
We hope so too. David, I have one question. I don't know if
Sure.
it's, but these bridges are from highways, right?
Well, yes, these are I guess what they call, these are non-highway bridges. Actually, these are not on the interstate.
Okay, well, but
Yeah, they're on the local roads.
roads, right? But it's the same. It's the same if we are analyzing a railroad bridge.
Well, let me tell you, that's a really good question, because so we finished a project a couple of years ago, because in New Mexico, the New Mexico DOT, there's a rail line
Yes.
in New Mexico, and it used to be owned by I think it was Burlington Northern Santa Fe, BNSF.
Yeah.
And they used to own it, and under a previous governor, the New Mexico essentially purchased the railroad. Okay, so now they have all these bridges on the railroad, because now they use it for transporting for passengers. Now it's called the Rail Runner, and it's located here in New Mexico. So there's a lot of bridges on that particular line. So there's a lot of steel bridges, a lot of pre-stressed concrete. And so we did some load rating on those, and we had to go back to historical documents, because on railroad bridges, the interesting thing there is they're very old. They're like built in the 1900s. So they're over 100 years old. And so on those, they have to go out and do some measurements and we did a couple of load tests on those bridges, but the idea is you have to do a lot of field visits. You have to go out to the bridge, take measurements of the dimensions of the girders, come up with an estimate of what the strength was, and then do an analytical load rating on those. But it's similar, the load rating is similar, it's just different in terms of the loading. You have to use the Cooper E80 loading. You also have to use different distribution factors, and also the dead load's different because you have the ballast, you have the the barriers, you have the rails, you have the ties. But you know, it's similar. You have dead load and live load effects. It's just different types of dead loads and different types of live load.
Okay. Yeah, well, thank you. That will be interesting to know more about that. Wow.
Sure, and yeah, and we did some. We actually one of my students did a thesis on that project. I'd be happy to share it with you. I'll send you a copy.
Oh, that will be great. Thank you, David.
You're welcome.
Okay. ¿Alguien más que quiera como última pregunta aquí para el doctor Jáuregui? Yo que ustedes aprovechaba, yo ya aproveché. Aquí
They can also ask me about the program if they feel they can ask me about the program if they wish also if they'd rather ask about that rather than the presentation.
Yes, David, we have one in the chat, so you can see it.
Yeah, let me see if I could. Okay.
Okay, thanks.
Okay. It has to do with validating the degree here, and so what they would have to do, if you want to validate your degree, what would happen is probably you'd have to go through what is called the New Mexico Society of Professional Engineers. Okay, so what they will do is they'll evaluate your degree, and then they will give you an opportunity to take the engineering and training exam, which is the fundamentals of engineering exam. Okay, and then once you take that exam and you decide they decide to work in the US, they can have to work for 4 years and then become in order to take the exam for the PE license. But there are procedures to do that, but you have to go through the board of licensing board. Okay, I hope that answers the question.
Okay. And we have another one in Spanish, David.
Okay, let me see. Okay. Yo estoy haciendo okay, so let me see if I could translate it in English. They're doing a thesis of using the AASHTO in Mexico. They have a problem with overloads. Is there similar problems? Definitely. Okay, so as I started at the beginning of my talk, let me see if I can answer this in Spanish. Okay, I'm going to do my best here. Pero sí tenemos el mismo problema. Hay sobrecargas y más en el sur oeste de Nuevo México. Están explorando aceite y gasolina abajo de la tierra. Están excavando gasolina y ese equipo es muy pesado y por eso hay sobrecarga. Entonces lo que nosotros estamos utilizando es inteligencia artificial y estamos tratando de conectar sobrecarga con deterioración de los puentes y también del pavimento. Este proyecto que tenemos vamos a terminar al finales de diciembre. Nos gustaría mucho a lo mejor poder colaborar, porque sí, este problema es muy común en Estados Unidos. Para darle una idea, la carga de diseño, vamos a decir que es como 80,000 libras. Las cargas que están pasando en la carretera son más de 1 millón de libras. Entonces está causando mucho daño a los puentes y por eso el Estado de Nuevo México quieren, vamos a decir, cambiar el proceso de los permisos. Al final quieren cobrar más para los vehículos que están entrando a Nuevo México para poder, vamos a decir, tener fondos para reparar los puentes y también el pavimento. Ojalá que eso, ojalá que contesté la pregunta. So the tests are just analyzing New Mexico area. That is correct. That is correct. These tests are just for New Mexico, but there are also other states that are also doing similar types of testing, like Alabama, Florida, Michigan. But the ones we're doing are just for New Mexico because it's very specific to New Mexico on the bridges that go over the channels.
Okay.
And yes, so the permits are also only for New Mexico.
That's great.
Yeah, and I'd be happy to collaborate. In fact, I'd be very interested on the student. It says here, Ivan. So if they would like to share their thesis, we'd love to hear about what they're doing. And that might actually be something where we could collaborate because we have Dr. Douglas Cortez, who's working on the pavement side, and we have another professor by the name of Dr. Neary, who's working on the bridge side. And we're just coming up with models to figure out how we're going to change our permitting structure. So this may be something that may be of use and maybe a future project that we could collaborate on.
That would be very, very nice to do that work with all of you. Okay, well, 5 o'clock.
Okay.
Bien, ya no hay más preguntas, creo yo. Vamos a hacer el cierre formal de esta presentación, la cual estamos muy, muy contentos de que se haya podido dar, porque la agenda del doctor Jáuregui pues está muy ocupada y pues nos hizo un huequito aquí a nosotros para darnos esta plática. Le agradecemos por su tiempo, participación, excelente conferencia y sobre todo por apoyarnos en este evento de seminarios de investigación de la Facultad de Ingeniería. La verdad es que es un honor para nosotros haber contado con su presencia. We are so honored to have you here and we hope to have you face to face very soon. Maybe here in Chihuahua or maybe we can go to NMSU.
We could do both maybe.
Yes,
Yeah.
will be great.
Yeah, and I also wanted to thank you once again, Dr. Espigel Garcia and also Dr. Villalobos Aragon. I really appreciate this invitation. Strengthening our collaboration is very important to me. We continue to build upon this relationship, and whatever I can do to help further it, I'm all for it. And also, please feel free to share my contact information with all the students. And I would be very, I'm really looking forward to going and meeting all of you. All I see is names, unfortunately. I see a lot of names on the screen, and I'd rather meet you in person and get to see you and talk to you about our program, and hopefully someday welcome you personally to our department. So, thank you.
Oh, thanks to
Thank
you.
very much.
Y aquí a todos los presentes les agradecemos por su asistencia. La verdad es que muy concurrida esta conferencia y de verdad que les agradecemos. Estén pendientes para la próxima semana que será sobre cementos, sí, para que estén pendientes. Por ahí pasaremos la difusión y muchísimas gracias por haber asistido y que pasen muy buenas tardes. Gracias a todos.
Gracias.
Gracias.
Gracias, David.
Gracias.
Gracias.
Hasta luego.
Buenas
Gracias.
noches.
Hasta luego.
See
Bye.
you soon. Bye bye.
Hasta luego, gracias a ustedes.
Muchas gracias.
Okay, David.
Daphne, when you have a chance, I'd like to, if you could, you're going to post it. Let me know when you post the presentation, and that would be great.
Yes, of course. Do you want if we can share the WhatsApp so it's easiest to me to send
Okay.
you the link and everything. Do you have?
Yeah, I have WhatsApp.
That's great. Do you want to share here or by email?
Oh, I'll share it by email. Yeah.
Okay, that's great.
Yeah, it's better because I'm probably gonna take forever to try to figure out how to do it.
That's great. So I will send you your paper to certificate you gave this conference here. So, and then you can share me your WhatsApp so we can stay in touch.
Okay, sounds good.
Thank you very much, David.
Yeah, thank you.
Have a good night.
Have a good rest of the night and have a good weekend and have a safe and happy Halloween.
Oh, you
And,
The
too.
same for you.
And a
The
good
same for
Dia
you.
de los Muertos also.
Yeah, of course.
The same for you. Bye-bye.
All right, bye-bye.
Bye.